a planetary model of the atom. Why do some elements and not others combine to form compounds? What part of an atom is involved when chemical reactions occur? Rutherford's nuclear model did not answer these questions. Also, the nuclear model itself had problems. Since electrons are negative and protons in the nucleus are positive, why didn't the atom collapse as the electrons were attracted to the nucleus? To answer these questions, another model was required. Look at the planetary model in Figure 1. How does this model resemble Rutherford's nuclear atom? Further experiments suggested that, as an improvement to Rutherford's model, electrons orbited around the nucleus like planets around the sun. Atoms and rainbows. What do atoms and rainbows have in common? Their behavior can be explained in terms of energy. When white light passes through raindrops or a prism, it is split into a spectrum. A rainbow of the many colors that combine to make white light, Figure 2, showing a narrow beam of white light is split by a prism into a continuous rainbow of colors: red, orange, yellow, green, blue, indigo, and violet. Different colors of light have different energies. For example, blue light has more energy than red light. When elements are heated in a flame, they show a few specific colors. Figure 3. When an element is heated in a flame, it produces only certain colors or energies of light. Each element has its own unique light spectrum. These specific colors seen through a spectroscope are called a line spectrum. How could these definite energies of light be explained? A Danish physicist, Niels Bohr, proposed a planetary model of the atom to explain line spectra. Bohr suggested that electrons move about the nucleus in nearly circular paths called orbits, like planets around the sun, Figure 4. Figure 4, in Bohr's model of the atom, electrons traveled around the nucleus in nearly circular orbits, much like planets around the sun. Each electron in an orbit has a definite amount of energy. The farther away the electron is from the nucleus, the greater its energy is. Electrons cannot exist between these orbits, but can move up or down from one orbit to another. The order of filling of electrons in the first 3 orbits is 2, 8, and 8. Electrons are more stable when they are at lower energy, closer to the nucleus. Bohr's model explains the spectra of elements in terms of the jumps that electrons make from one orbit or energy level to another. Figure 5. Figure 5, imagine an electron in Bohr's model as being like a marble on a staircase. The marble can only be at certain definite levels. It can jump up or fall down by only very specific amounts. In this model, electrons are arranged in orbits that surround the nucleus like layers of an onion. Space in the orbits is limited, and the electrons are arranged in a definite pattern. Within the orbits, electrons move quickly. When electrons are energized by heat, electricity, or light, they use this extra energy to jump out to a higher orbit. Figure 6. Figure 6, an electron jumping out of its regular orbit. Very, very important figure. Study Figure 6 carefully. We say they are in an excited state. The excited electrons are very unstable and tend to fall back into their normal, more stable orbits. This low energy state is called the ground state. When the electrons drop back to their normal orbits, their extra energy is given off in the form of light. The amount of energy given off is equal to the difference in energy between the higher and lower energy levels. This very specific energy amount corresponds to a very specific color. Bohr's model of electrons in energy levels also explains why each element has a different spectrum. For example, hydrogen has only a single proton and a single electron. Sodium has 12 protons and 11 electrons. The orbits in these two atoms are at different distances from the nucleus. Therefore, the energies of the electrons in the two atoms are slightly different. An electron jumping from the third level to the second level in a hydrogen atom may produce a red color. The color is evidence of the difference in energy between the two levels. An electron jumping from the third level to the second level in sodium atom may produce a yellow color because the orbits are at different distances from the nucleus. The Bohr model of electron arrangement. Bohr developed his model of the atom to explain the line spectrum of hydrogen, but it was soon extended to other elements. Scientists drew Bohr diagrams to represent the electronic structure of elements. In these diagrams, the symbol of the element is written in the center to represent the nucleus of the atom. A series of concentric circles are drawn around the nucleus to represent the orbits, and electrons are shown in these orbits. The element hydrogen, which has an atomic number of 1, has 1 electron in its first orbit. The element nitrogen, symbol N, which has an atomic number of 7, has 7 electrons. 2 electrons are in the atom's first orbit, and the remaining 5 are in the second orbit. Phosphorus, symbol P, with an atomic number of 15, has 15 electrons. 2 electrons are in the first orbit, 8 are in the second, and 5 in the third. Figure 7. Bohr models of electron arrangements for hydrogen, nitrogen, and phosphorus. Bohr-Rutherford diagrams. We can combine Rutherford's nuclear model with Bohr's planetary model in diagrams that summarize the numbers and positions of all 3 subatomic particles in an atom. In these Bohr-Rutherford diagrams, a circle is drawn in the center to represent the nucleus of the atom. The numbers of protons and neutrons are written in the circle. Electrons are again shown in circular orbits about the nucleus. For example, consider a Bohr-Rutherford diagram for magnesium, Mg24. The atomic number of magnesium is 12 and its mass number is 24. Therefore, there are 12 protons and 12 neutrons in the nucleus. Mg24 has 12 electrons, 2 in the first orbit, 8 in the second orbit, and 2 in the third orbit. Similarly, chlorine-35 has 17 protons and 18 neutrons in the nucleus. 2 electrons in the first orbit, 8 electrons in the second orbit, 7 in the third orbit. The Bohr-Rutherford diagrams for these atoms are shown in Figure 8. Bohr-Rutherford diagrams for magnesium-24 and chlorine-35. The electron arrangements can be described as 2, 8, 2 for magnesium and 2, 8, 7 for chlorine. Electron arrangements in ions. Recall that atoms can lose or gain electrons to form charged atoms, ions. But which ions do atoms form? In Bohr diagrams for the first 20 elements from the periodic table, there is something special or stable about the numbers 2, 8, and 8. Many elements tend to form ions by losing or gaining enough electrons to have 2 or 8 electrons in their orbits. For example, look at the atoms in Figure 9 and compare them with Figure 8. A magnesium atom becomes an ion by losing the 2 electrons in its outermost orbit. The ion has 2 electrons in the first orbit and 8 in the second. It also has a +2 charge because it has 2 more protons than electrons. Chlorine forms an ion by gaining 1 electron. The ion has 2 electrons in the first orbit, 8 in the second, and 8 in the third. It has a -1 charge because it has gained an extra electron. Understanding concepts. What is meant by the term spectrum? B. How is the spectrum seen in a rainbow different from the spectrum of an element? 2. A. In words, describe the structure of the atom using the Bohr-Rutherford model. B. What paths do electrons follow in the Bohr model? Why are orbits also called energy levels? And last, D. How do the energies of electrons in different orbits compare? 3. A. How does the Bohr model of the atom explain light given off in line spectra? B. Why do different elements produce different line spectra? 4. Draw Bohr diagrams for A. Oxygen, symbol O, atomic number 8. B. Aluminum, symbol Al, atomic number 13. Calcium, symbol Ca, atomic number 20. Draw Bohr-Rutherford diagrams for A. Fluorine, 20, symbol F, atomic number 9. Boron, 11, symbol B, atomic number 5. Potassium, 40, symbol K, atomic number 19. 6A. Draw Bohr-Rutherford diagrams for the stable ions formed by gain or loss of the electrons in each of the atoms in the previous 2 questions. B. Write the symbol and charge of the stable ion formed by each atom. 7. For atoms to interact, they must collide with each other. Which subatomic particles do you think has the most important role in chemical change? Explain why. 8. Look at the tables of combining capacities on page 64-65 and your answers to question 6A. Which elements are named in both the table and the question? B. Compare the combining capacity and the charge of the ion for each of these elements. What pattern do you notice? And 9, reflecting. Draw a chart to help you organize and remember what you need to know to draw Bohr-Rutherford diagrams. 3.5 Investigation. Using electrons to identify elements. Now we will do this investigation, and what you'll need to do is look up YouTube to find out colors of flames. And watch the flames relative to the chemicals that are put in the flame. According to the Bohr model of the atom, when the atoms in an element are provided with energy, some of the electrons may jump up to higher levels. This energy can be in the form of heat, light, or electricity. The electrons are said to be in an excited state because they are in higher energy orbits than normal. The electrons then tend to fall back down to their normal lower energy level or ground state. When this happens, the atoms give out energy in the form of light. Since different elements have slightly different energy levels, different energies or colors of light are given out. Figure 1. A. Sunlight produces a continuous spectrum of light corresponding to many different energies. B. An element like hydrogen produces only a certain energies of light that correspond to electrons dropping to lower energy orbits. These colors are like the fingerprints of elements, especially metals, even when they are combined with other elements in chemical compounds. In this investigation, you will use an experimental technique called a flame test. You will heat samples of a compound and determine the identity of the metal in each. Figure 2 shows an alternative method for conducting a flame test. Another way to do flame tests is to dip a loop of platinum wire into a solution and then into the flame. Some of these solutions are poisonous. Any spills of these solutions on the skin, in the eyes, or on the clothing should be washed out immediately with cold water. Inform your teacher of any spills. Materials: goggles, apron, Bunsen burner, flint lighter, 8 250 milliliter beakers, each containing 1 splint for each student group. Each splint soaked in 0.5 moles per liter solution of one of the following: lithium nitrate, sodium nitrate, potassium nitrate, barium nitrate, calcium nitrate, copper nitrate, and 2 unknown metal nitrates. Beaker containing water for extinguishing splints. Question: what can be observed when various compounds are heated in a flame? Hypothesis 1. Write your own hypothesis about what you might observe. Procedure: design an observation table in which to record what you see. 3. Review the safety procedures for using a Bunsen burner. Put on your apron and safety goggles. 4. Obtain from your teacher 8 wooden splints that have been soaked for 2 to 4 hours in solutions of 6 known and 2 unknown compounds. Only the bottom halves of the splint have been soaked. Handle the splints by the dry ends only. 5. Use the flint lighter to ignite the Bunsen burner. Adjust the burner to produce the hottest possible flame. 6. Hold the soaked end of the lithium nitrate splint in the flame for a short time. As soon as the flame is no longer strongly colored, extinguish the splint by placing it in the beaker of water. Record your observations of the flame color for lithium in your data table. Do not burn the splints. 7. Repeat step 6 for each of the other 5 known solutions. Record your observation of the flame color for the other metals in your table. Repeat step 6 for the 2 unknown solutions. What do you think is the identity of the unknown solutions? Record your observations of the flame colors for the unknown metals in your table. 9. Return the splints as directed by your teacher. Clean up your workstation and return your apparatus. Wash your hands. Analysis and communication. Analyze your observations by answering the following question. What was the identity of each of the unknown solutions? How did you decide? B. Which metals were easy to identify? Explain. C. Which metals were difficult to identify? Explain. D. Why were all the compounds you tested nitrates? 11. Write a lab report for this investigation. Understanding concepts. What is the significance of conducting flame tests? Explain how you might test a sample of unknown white solid to determine if it was table salt, sodium chloride. Remember that a taste test is never recommended. Exploring. Design an investigation to answer the question, what chemicals are used to make the flame colors of burning fire logs? Conduct the investigation and report on your findings if your design is approved by your teacher. Your teacher may have cardboard spectroscopes available to view the spectrum of each element. Describe the so-called line spectrum that you observe. How would this line spectrum be more useful than a simple flame test? Isotopes and radioisotopes. The discovery of isotopes and radioisotopes has changed our lives in many ways. We now have sophisticated medical equipment, nuclear waste, and an ongoing debate about nuclear power. An isotope is any of 2 or more forms of an element, each having the same number of protons, but having a different mass due to a different number of neutrons. For example, chlorine has 2 common isotopes. Each has 17 protons, but some atoms contain 18 neutrons, and others contain 20 neutrons. Thus, one isotope of chlorine is called chlorine-35, having an atomic number of 17 and a mass number of 35, 17 protons plus 18 neutrons. The other isotope of chlorine is chlorine-37, has an atomic number of 17 and a mass number of 37, 17 plus 20. Hydrogen has 3 isotopes, figure 1. The 3 isotopes of hydrogen have the same number of protons but different number of neutrons. The one with no neutrons is the most common, and they are A, protium, that has 1 proton and no neutrons, deuterium, 1 proton and 1 neutron, and tritium, 1 proton and 2 neutrons. Isotopes of the same element have the same physical properties and the same chemical properties. They undergo the same reactions. However, some isotopes are unstable or radioactive, which means that the nucleus has a tendency to break apart and eject very high energy particles into its surrounding. Figure 2. The symbol indicates that a radioactive substance is present and should be handled with care. The huge amount of energy these particles have can be both dangerous and useful. Atoms that have unstable nuclei are called radioisotopes. Types of radioactivity. Radioactivity was discovered accidentally in 1896 by a French scientist, Henri Becquerel, when he was studying a sample of uranium. He found that the uranium could produce an image on photographic film even when the film remained sealed inside its package. Some of the unstable uranium nuclei split apart or decayed, producing particles that went right through the package and reacted with the film. Over the next 7 years, 3 different kinds of radioactivity were identified. Figure 3. The 3 types of radioactivity have different penetrating power. Gamma rays are the most dangerous and can only be blocked by thick sheets of concrete or lead. They were named alpha, the Greek letter alpha, and beta, the Greek letter beta, particles, and gamma, the Greek letter gamma, rays. Alpha particles were later found to be helium nuclei containing 2 protons and 2 neutrons. Beta particles are high-energy electrons, and gamma radiation is high-energy electromagnetic radiation with no mass. Applications of radioisotopes. Radioisotopes must be treated with caution because they can damage living tissue. They may alter the DNA, which affects how cells divide. This can cause serious diseases, including cancer and birth defects. However, radioisotopes are very useful when used carefully by qualified doctors, scientists, and technicians. A few of the many applications of radioisotopes are shown in Figure 4 to 6. Figure 4. Radioisotopes are often used to diagnose medical problems such as thyroid disease. Doctors inject the radioactive isotope iodine-131 into the body, and the blood carries most of it to the thyroid gland in the neck. Technicians can then take a photograph of the neck to see the size, shape, and activity of the gland. Figure 5. Archaeologists use a technique called carbon-14 dating when they want to know the age of ancient humans and their artifacts. Carbon dioxide in the atmosphere naturally contains a measurable amount of carbon-14, which is absorbed by plants in the process of photosynthesis. It is then incorporated into the bodies of animals that eat the plants. This reindeer bone was discovered in a glacier. During the years since the animal's death, the bone's carbon-14 steadily decayed. When scientists test the bone, they measure the amount of carbon-14 left. They then calculate the length of time since the animal died. Figure 6. You probably have a radioisotope in your home. Some smoke detectors contain a tiny amount of the radioisotope americium-241. The radioactive particles charge air molecules so that a small electric current flows. When smoke enters the detector, it interferes with this current and the alarm sounds. Understanding concepts. What is an isotope? 2. What is meant by the term radioactivity? Give an example of a radioisotope. 3. Represent the following radioisotopes using standard atomic notation. How many neutrons does each have? Technetium-99, atomic number 43, cobalt-60, atomic number 27, carbon-14, atomic number 6, iodine-131, atomic number 53, americium-241, atomic number 95, uranium-235, atomic number 92. Making connections. Describe 4 useful applications of radioisotopes. What are their risks, if any? 5. Visit your local medical center or dentist to find out how X-rays are produced. Find out what steps medical professionals take to protect themselves and their patients from radiation. Fireworks. Electron jumps in action. What creates the colors in fireworks? A modern fireworks shell contains black powder that burns to propel the firework up into the air. The shell also contains separate packages of chemicals that produce special effects, such as bursts of colors, flashes, and sound. Some of these materials are described in Table 1. Each firework explosion is a carefully controlled series of chemical changes that occur at just the right times. These chemical changes produce large amounts of heat, which make electrons in metal atoms jump up to higher energy levels or orbits. When the electrons drop back to normal ground state in orbits nearer the nucleus, they give off energy, including bursts of colors. Making fireworks is hazardous and should be attempted only by well-trained professionals. Inside a fireworks shell, suppose a pyrotechnic technician had the job of making a fireworks shell that would rise 50 meters and then produce a red burst of fire followed by a loud bang and flash. The technician would have to make 3 different explosive mixtures, 1 to lift the shell into the air and 1 for each of the 2 special effects. Figure 1, a fireworks shell. So there's the shell, and here we have a mixture of potassium chlorate, strontium carbonate, and paraffin oil. And in the other cell, we have a mixture of potassium chlorate, sulfur, and aluminum. And then in the last one, we have a mixture of potassium nitrate, sulfur, and charcoal. So 1, the technician lights the first fast-burning fuse, A, which causes an explosion that launches the shell into the air as the black powder explodes. 2, fuse A also lights a slow-burning fuse B, which ignites a mixture that produces the red burst when the shell is high in the air. 3, the red explosion lights another slow-burning fuse C, which ignites a mixture that produces a final flash and loud bang. The first and most dangerous step is mixing the ingredients. As in other combustion reactions, the ingredients needed in fireworks include a fuel, a source of oxygen called an oxidizer, and a source of heat to start the reaction, a burning fuse. Typical oxidizers are potassium nitrate, potassium chlorate, potassium perchlorate, and ammonium perchlorate. Each mixture also contains binders like red gum, paraffin oil, or dextrin. The binders act as fuel and hold the mixture together. The technician then wraps each mixture in a cardboard package and links the packages with fuses. Did you know The history of fireworks pyrotechnics began in China 1,000 years ago with the discovery of black powder, gunpowder, a mixture of potassium nitrate, saltpeter, charcoal, and sulfur. At the time, people used saltpeter to preserve meat. They may have found, by chance, that a mixture of charcoal, iron, and saltpeter produced sparks when sprinkled into a fire. When this mixture burns, it produces large amounts of gases and energy in the form of light and heat.